Hi class, I'm back with Unit 2, and hopefully the video from Unit 1 you found helpful. And I'm going to pick up here with Lesson 2A, which is on doubling population. And the first question that is asked here is, what does the entry 8000 BCE mean in this table? So let's just take a look at this table. We've got the years here, and it's actually split table because it was so long, so we have continued the years over here, and then we have the world population, which of course back in these later dates would be an estimate. Now we have a little bit better ways of, it's still an estimate, but a little bit better ways of estimating it. And these are the populations for the last few years. It's important to note up here that it says that this is a lower bound in millions. So when you see this number 1, that of course doesn't mean there was one person in the world. That means there was 1 million people in the world. 9000 BC, 3 million people in the world, and so on. And what that means is basically that if we were to write this number down as a regular number, that we'd have to add 6 zeros to the end of it, because a million has 6 zeros in it. So we'd have to move the decimal place over 6 spots. Which in this case, since these are all whole numbers, would mean adding 6 zeros. So what does 8000 BCE mean? Well, the BCE means before Common Era. So it used to use the initials just BC a lot, which a lot of times people would take to mean before Christ. And it does have some indications with the Christian religion. According to the Christian religion, they believe Jesus lived in this time period, or was born in this time period, between the BCE and the AD. And so, but it's been kind of changed so that it doesn't specifically reference Christianity. And these dates, you'll notice, get smaller as you go up, or as you go down the list, because this is kind of like the negatives on a number line. 500 BCE would be after 1000 BCE. So it's kind of like negative. So when you say 10,000 BCE, that's like 10,000 years before the Common Era, whereas 1000 BCE is only 1,000 years before the Common Era. So that's what the BCE means. We are, of course, in the Common Era, in the AD years. And so 8000 BCE, if we were to, to calculate that, now we're in, I'm going to say 2000. I know it's 2017, but say we're in 2000. If we go back to AD, that would be 2000 years ago, because that's 2000 AD. And then if we add back 8000 years, so 8000 BCE is actually 10,000 years ago. Okay, so now I've pasted in the questions from the next page. I'm trying to keep these questions in this table up at the same time. So question 2 says, how long did it take for the population to reach double that amount? So in 8000 BCE, it said that we were at 5 million. So what we're looking for here is we're looking for a double from that 5 million. And so from 5 million to get to 10 million took from 8000 BCE to 6000 BCE. So that would be 2000 years. So I'll write that down. So 2000 years. And then that was from 8000 BCE to 6000 BCE. Okay, and it took from 5 million to 10 million. It's always good in your notes to have this fairly clear so that you don't have to come back and reinvent the wheel because you aren't sure what you wrote down. So how long did it take for the population to double again? So if we go over here and we look, Okay, so we were at 5 to 10. Now when we say double again, do we mean to get to 15 million? And the answer to that is no. It says to double again. So we went from 5 to 10, and we're not looking to add another 5 million. We're looking to double that number. So from 6,000 BCE to double, it took till 4,000 BCE. So again, if we write that over here, it took us 10 million to 20 million. Took from 6,000 BCE to 4,000 BCE. So that took, of course, 2,000 years. Okay, so the next question says, find at least 3 other examples of doubling population in the table. Now, it specifies here that it doesn't have to be exactly double. For example, Earth's population doubled between 500 BCE and AD 1, which was a period of 500 years. And it does not have to be exactly double. So if we pick a number over here, say, these are some more unusual numbers because they're more accurate estimates, we're not going to find something that's exactly double that. So we're just going to look for things that are close to double. So I'm going to pause here a minute and erase what we have written so we have some room to write. Okay, so now that we're back to our clean slate, let's look for some time periods where it doubled besides the ones that we already talked about. So I'm just going to pick a year. We'll pick one that's relatively easy. Of course, we've already talked about this one, so we don't want to do that. So let's say I pick this year right here, or this number. If I want to look for when that's doubled, this is 25 million. So to double, it took it until 50 million. So another one would be, and I'm just going to indicate that over here. So from 25 million to 50 million, and that took, again, 2,000 years. So did it always take 2,000 years to double? And the answer is no. Well, we already know that it took it from 500 BCE to 1 AD, which is kind of like 0, but they don't really technically have a 0 year. That took it only 500 years. And if we go over here and we look for some doubling instances, 1960, for instance, was at almost 3,000, which again is not 3,000, it's actually 3. Let me write it out. So it's 2982, and then that would have 6 zeros after it. Okay. So this would be 982 million. So this here is 2,982,000,000 people in 1960. So if you say, well, that's roughly 3 billion people, then we're looking for it to be roughly 6 billion people, which would be about here. Okay, and it's not perfect, but that's how long it took to be close to from what's in our table to double. So how long did that take? Well, it looks from the table like it's a longer time period, but you notice over here on this side we were going by thousands, and then we went by 500, and then we went by 1,750, and then we went by 50, 50, 50, 50, 10, 10, 10, 5, 5, 5, 5, 5, 5. So they started making the years closer together. So even though this looks in the chart like it's further apart, it's actually only 1960 to 2000. So that one is only 40 years. Okay, whereas over here we were 2,000 years and 500 years. So let's pick another one. One that's interesting because it splits across the table. A lot of people don't like to do that. If we pick, say, right here in 1750, that's about 800. So when does it take to double? Right here. So from here to here doubled also, and that's from 1750 to 1900, which is about 150 years. And again, it's not exact. There's no, if we were going to double that exactly, it'd be different than 1,650, but if we consider this to be close to 800 and this to be close to 1600, then that's a close to doubling. So the biggest thing here is it didn't take a consistent amount of time to double. It got quicker and quicker as the years went by to get a doubling amount. You know, up here it was taking 2,000 years, and then 500 years, then 150 years, and then in this area it only took 40 years. So we've completed 4 here. It says now discuss your results with your group. Was the doubling time always the same? The answer is no. It got shorter and shorter as we went along. What does that tell you about the rate of growth? So if the doubling time got shorter, does that mean that the population was growing slower or more quickly? Well, if it's doubling in a shorter amount of time, that means that it is growing more quickly. So the population is growing more quickly now than it was back in the BCE era or even the early AD era, or early AD time period. So which of the following statements best describes the change in doubling times before 1750 AD? The doubling times generally decreased. Before 1750, estimated population doubling times decreased from 2,000 to 500, or the doubling times decreased from 2,000 to 1,000. Well, this one makes the most sense because we saw up here it was pretty consistent that it was doubling every 2,000 years, and then here it only took 500 years, and then it took another 500 years, and then we don't know here, they don't have 500 AD, so, but it was definitely decreased from 2,000 years initially to 500 years by 81. So write a statement that describes the change in doubling times after 1800. So we're going to go on this side of the table, and we can look at again some of these time periods from 1800. That was almost 1,000, and 1,000 million, which would be 1 billion. And then we don't have a perfect double time here because we're looking for about 2,000 because that's close to 1,000. We don't have anything here that's close to 1,000, so it was somewhere around maybe 1925. So it took maybe 125 years. This one that we talked about here took 150 years. But then as we got up here, it decreased. So we're going to try to write a sentence that's similar to what they have here that kind of describes that. So we'll say, after 1750, estimated doubling times decreased because the population was increasing more quickly, so the time to double decreased from about 150 years to less than 40 years. So I just kind of went off of what they had here and filled in with the new information from the other side of the table. Okay, so for number 7 it says write a statement that describes the change in doubling time. Whoops, that was that. Sorry, this was number 7. Number 6 was just to pick the multiple choice. So we're on number 8. What are some factors you think may have led to this change in doubling times? Well, why is the population doubling more quickly? It's a lot of factors play into that. And one of the main factors is just healthcare and things like that. Things that that cause people to be able to live longer. And so, you know, we're not getting eaten by animals as often as they were, say, back in the BCE era. We're not fighting for, you know, we're not having to fight as much for clothing and things like that. Of course, there's still a lot of people in the world that are in poverty, but, you know, this was a time period where everybody was living in the wild rather than living in substantial shelters and such. So you could say shelter is better, medicine or medical advancements, things like that. So all those things that help people to live longer that have developed. So advancements in helping people live longer. It says, imagine that you're explaining the relationship of million, billion, trillion to someone else. You may use words, symbols, and pictures. Your response should follow the guidelines. So here they would just be talking about, like, how would you explain the difference between a million and a billion and a trillion to someone? Well, if you have a million, and we want to compare that to a billion, and then compare that to a trillion. I'll go back and put commas because it makes it easier to read here. What happens each time we add one more period? Well, what that does is it adds 3 more zeros to it, and that's because the number has been multiplied by 1,000. So a billion is 1,000 times bigger than a million. A trillion is 1,000 times bigger than a million. And so you could describe it that way, or you could describe it with the number of zeros. A million has 6 zeros, a billion has 9 zeros, a trillion has 12 zeros. And so we'll just leave it at that for now. And we'll move on to lesson 2B. So now we're going to talk about scientific notation and how to write numbers in scientific notation. So it says, refer back to your lesson 1, part A. And, I'm sorry, I need to discuss this. So it says there's this many different ways to deal a 52-card deck. And this is just one number here. That's how many different ways there are to deal a 52-card deck, if you can believe that. And of course, this is a quite large number. In fact, it is so large that it's almost impossible to get an idea of how large it is. And so one way to express really, really large or really, really small numbers is to use scientific notation. So to use scientific notation, we think about the number using multiplication, and specifically we talk about it as a multiplication by a power of 10. So we're going to go back and think about our lesson that we had before. And we're going to assume that the average shoulder width of people on the line was 1.325 feet. We actually used 1.5 feet, but we'll use the number that they have here just to stay consistent. So it says, how long would the line be if it contained 10 million people? So if we have 1.325 feet per person, and we wanted to have 10 million people in the line, then we're going to take this number times 10 million. Now, what is 10 million? 10 million would be 10 with 6 zeros. So a total of 7 zeros because you have a 0 with the 10. So this is 10 million. So you're taking 1.325 times 10 million. What this would do, again, the zeros help you decide how many decimal spots to move. Since there's 7 zeros, it would move this decimal right here to the right 7 places. Now, again, if that's bothersome to you, I'm never going to take your calculator away from you. You could also type it into the calculator. So 1.325 times 10, 2, 3, 4, 5, 6 times 10 million would result in 13,250,000. Again, that's just taking the decimal that was here and moving it 1, 2, 3, 4, 5, 6, 7 decimal places. So we have 13,250,000 for our answer there. Now it says round the answer to the nearest million. Okay, so the nearest million would be this spot. So they want us to round this number to this spot. So when you're rounding, you're just trying to decide, do I leave this as a 3 or do I round it up to a 4? And the number to the right of it will tell us what to do. So since this is a 3 and this is a 2 to the right of it, the 2 says leave it alone. We only round up if this number is 5 or bigger. So we're going to leave this as a 3. So rounded, we're going to call that about 13 million. And yes, we rounded that down, so we lost the 250,000 in there, but it says to round it to the nearest million. So how many zeros are in this number? Well, there's 6. zeros in that number. And we're supposed to rewrite this answer using multiplication. So we're not going to quite use scientific notation yet, but we're going to think of this as a multiplication. So you could think of that as 13 times a million. So 13 million is 13 times a million. And it says think of different ways to express the number and write it down. So there's some different ways we could do that. We could think of it in word sense, like we did in the table from the last lesson, 13 million. We could shift the decimal over one spot and think of it as 1.3 times 10 million. That's pretty similar to what we started with up here. And there's a variety of different ways. So the idea here was just to have you work with your group and discuss some different ways. So one thing that we want to talk about, though, before we go on to the next thing here is powers of 10. So I'm going to kind of just do a little aside here. A power means that we're going to multiply that number, that many factors of that number. So 10 to the first literally just means 10. 10 to the second means 10 times 10, which would be 100. 10 to the third means 10 times 10 times 10, or 1,000. So you notice, however, whatever the power is, if it's got a base of 10, you have that many zeros. So 10 to the second has 2 zeros, 10 to the third has 3 zeros, and so on. And those zeros, again, make the decimal spot move. So if we wanted to work on, some of these things, I could think of this as 13 times 10 to the sixth. And that's a little bit closer to scientific notation, although it's not quite in scientific notation yet. So going to the next page here, we have a little diagram of what scientific notation is. A scientific notation is when you take a number A and you multiply it by a power of 10, so 10 to some power up here. There's some constraints on this, though. The A has to be between 1 and 10, but not as big as 10. In other words, this A has to be somewhere between 1.0 something. It can have more digits than that, up to 9.9 something. Again, it could be 9.97. It just can't be a 10. There has to only be one digit in front of the decimal, and that digit can be from 1 to 9. It can't be a 0 in front here, and it can't be a 10 or bigger in front. Okay, and then we're going to multiply it by a power of 10 in order to get the correct number that we're dealing with. So is the answer to question 4 in scientific notation? And the answer is no, it's not, because here we have in word form. Here we have 13, so that's too big because it's above 10. And here this isn't a power of 10. So out of these, this is the closest one, so we're going to work with this. But the answer is no, none of these are in scientific notation yet. It said, use what you have learned to express the number of ways a 52-card deck can be shuffled. This is just a mean question. I'm not even going to bother with it. They want us to take that number that we had in the prior one, that big, long number about how many ways there are to shuffle a 52-card deck, and write it in scientific notation. It's ridiculous. It's a very large number. If you want to look back at that that page, it started out with 80658. You'd have to start with on that. So the answer to this was no. And here you'd have to start with 0658. So you might do 8.607. How many decimal points you take this out is kind of up to you. And then we'd have to take times 10 to some power. And I don't even know how many that has in it. It has like 40 some digits or something. So it would be, however, if we count from after the 8 all the way to the end of the number, that's what you would put here. But again, that's just kind of cruel to make us sit there and count all those digits. So we're not going to mess with that. Okay, so let's go up here and answer number 7. Just forget to switch back to my pen when I do things. Alright, so for number 7, it says, how does expressing this number in scientific notation change the way you understand it? So they're talking about this number. I think it emphasizes how big that number really is, that we'd have to count all the digits all the way to the end of that number and get some 40-some number up here. And so I think it just emphasizes how large it is. And that's what they were going after here without us having to sit and count all those digits. So it emphasizes the size, how large it is. Okay, so the chances of an event happening can be described using probability. For example, there's 1 in 2 chance of having a baby girl, which is the same as 1/2 or 0.5. So the probability of having identical twins is approximately 35 10,000ths. Express that number in scientific notation. Okay, I'm going to pause here because they never did have us do, once in a while they do weird things in this book. We're going to go back here and write this in scientific notation since we never did have it written in scientific notation. So let's start with that before we go on to that other number. So we have 1.3 times 10, and this first part is good because again it's between 1 point something and 9 point something. So we have 1 as a single digit here in front. And then we have 10 million here, which has 7 zeros. So in scientific notation, this number would be 1.3 times 10 to the 7th would be that number in scientific notation. We wouldn't want to do 13 because that doesn't fit the criteria of being between 1 point something and 9 point something. And we want to make sure that this indicates how many spots we've moved it. So remember our original number was 13 million. And if we count to go from here to behind the 1, that's 1, 2, 3, 4, 5, 6, 7 decimal spots that we moved. So that's where that 7 comes from. So before I do number 8, I'm actually going to, again, kind of go off here to the side and do a couple extras. So let's take a couple more numbers. So say you have the number 5, 6, 0, 0, 0, 0, 0. I will throw a couple more zeros on there. Say you wanted to put this in scientific notation. Okay? Well, first of all, you have to decide where are you going to put the decimal point. The decimal point is going to go after the 5 because we need a single digit in front of the decimal. So it's going to be 5.6. Then we have to count how many spots would we have to move the decimal from the end to between the 5 and the 6, or from the between the 5 and the 16. Doesn't matter which way you count. But it would take us 1, 2, 3, 4, 5, 6, 7, 8, 9 in this case. So that would be 5.6 times 10 to the 9th. Put another number up here. So say we had 4, 3, 8, 9, 1, 1, 0, 0, 6, 2. I'm kind of stuck on that length of number. Let me throw a couple more digits in here. Alright, so say we had this number, which would be 734,789,110,062. If we're going to write this in scientific notation, we're not going to keep all these non-zero digits because that's the point of scientific notation, is to have a shorter version of it. So I'm going to go here and I'm going to say, okay, I'll need my decimal point here. So it's going to be 7.3. And I could, this is up to you again. You can do 7.34, 7.343. You have to watch your rounding. If this was a 5 or higher, I'd have to do 7.4. So you have to watch that rounding. I'll do another one here in a minute that has that. Then we have to again count. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 spots that we moved. So this would be 7.3 times 10 to the 11. And again, it's approximately. It's rounded because we lost some of those digits. So let me do just a short one, but that has some rounding to it. So let's say you had 5, 8, 2, 0, 0, 0. Okay, and we wanted to put that in scientific notation. That would be, it's not what I meant to do. Hold on a second. Let's say 6, 5, 8, 2, 0, 0, 0. Okay. So if I wanted to put this in scientific notation, I might say, okay, I just want to go one decimal past. I could do 6.6 something. I could do 6.58. I want to round it here. Well, if I'm going to round it to this spot, I can't say 6.5 because there's an 8 after the 5. And so if I wanted to round this, it would be 6.6 times 10 to the 1, 2, 3, 4, 5, 6 to the 6th power. That's kind of interesting. So I got 1, 2, 3, 4, 5, 6 times 10 to the 6th. And again, this 5 has to round up to 6 because it has an 8 after it. If this was 6.52, 6.53, we could leave it 6.5, but because there's an 8 after it, that 5 has to be rounded up. Okay, so now let's go back to the number that they had. They had the number 0.0035, and they wanted us to express that in scientific notation. Well, all the numbers that we had here were large numbers that we wanted to write in scientific notation. This is a small number that we want to write in scientific notation. So we're going to put the decimal spot here, so it's 3.5. But if I say 3.5 times 10 to the 1, 2, 3, that means 3500. That would mean 1, 2, 3. That'd be 3,500. And that's not what I want. I want 0.0035. So how do you indicate that? Well, you put a negative up here. A negative on the exponent would move the decimal the opposite direction. So times 10 to the negative third is like times 1 over 1,000 instead of times 1,000. You don't really have to worry about that. But just remember that negative numbers are for the negative powers are for the small numbers. And if it has a positive power, that was a big number. That was a large number, a number bigger than 10. If the number is smaller than 1, then we're going to have a negative number here, and that indicates that the decimal doesn't move to the right. If you were to take it out of scientific notation, it would move to the left. And then in this case, it's hard to see the number that they have there. Let me erase a little bit so we can see it. Oh, I just erased the whole thing. Let's undo that. All right, it's hard to see, but it's 7.56 times 10 to the 4th. And so in this case, instead of going into scientific notation, they want us to go out of scientific notation. And so if we start with the number 7.56 times 10 to the 4th, and we want to take that out of scientific notation, first we want to note that's a positive 4. So that means that we started with a large number. This was originally a large number. So it's 756. The decimal point is here in scientific notation, but we want to move it 4 spots. So we're going to go 1, 2, 3, 4. And that becomes 75,600 as a regular number in just what they call standard form. So in standard form, that's 75,600, which is the same as 7.56 times 10 to the 4th. So let me do one real quick that they don't have on here, but we'll do one that starts out in scientific notation with a negative power. And so, again, I'm just making this up. This isn't one that was originally on the lesson. Oh, goodness. I just erased all that. Just a second. All right, so if we go back to pick a number that's in scientific notation but has a negative on it. So say it was 9.14 times 10 to the negative 6th. Then that would mean we would take this decimal and we would move it 6 spots. But because it's a negative 6, we're not going to move it 6 right. We're going to move it 6 left. So it's going to go once around the 9, and then we have to, so that's 1, 2, 3, 4, 5, 6. So that's going to give us 5 zeros in front of that. And again, the reason it's not 6 zeros is because we have to get around the 9 before we continue to count. So there's 1 to get around the 9, 2, 3, 4, 5, 6. And so 9.14 times 10 to the negative 6 is 0. And that 0 in front is optional. I just like to put it because it makes it more obvious. So it's 0.012345 and then 914. So we moved it 1, 2, 3, 4, 5, 6 spots to take it out of scientific notation. So this is that number, that 9.14 times 10 to the negative 6 in standard form would be that. Okay, so picking up with lesson 2C, it says in previous lessons we analyzed how quickly Earth's population is growing. Rapid population growth can impact sustainability. That is, the Earth's ability continues to support human life. Sorry, apparently I can't speak. So we're looking at that, how the population growth is impacting sustainability. So our first question here is, in 2011, the population of the United States was approximately 311 million and the world population was about 7 billion. We want to write a ratio comparing the U.S. population to the world population as a fraction. Think about how you could simplify that. So if we write the U.S. population is 311 million. I'm just going to write it out with the word right now. And then the population of the world was 7 billion. So that's a ratio comparing U.S. to the world. I'm just going to write that here so we remember where it came from. Okay, so there's a U.S. population and the world population. So if I want to simplify that, it's kind of hard to simplify with these words here. So I'm going to write this out as the full standard number. So 311 million would move the decimal 6 spots, or in this case add 6 zeros. 7 billion would be 7 with 9 zeros after it. So how can we simplify that? Well, when you're talking about fractions, you can always simplify an entire period if you can cancel it from one to the other. So I'm going to cancel 3 zeros here, another 3 zeros here, and I could think of this as being 311 to 7,000, and that's a more simplified version. We don't have to deal with all those zeros. But what does that mean? Since the ratio is a comparison of part of the world population to the total world population, it can be written as a percentage. So what this means is that for every, I'm going to write this down because I don't really actually ask it, but I want to say it. What this means is for every 7,000 people in the world, so if you took a sample of 7,000 random people in the world, on average 311 are from the U.S. So if you took 7,000 people in the world, 311 of those people would be from the U.S. And it says we want to write that as a percentage. And we haven't talked about this yet, but to calculate a percentage for this, all we have to do is do 311 and divide it by 7,000. So as a percentage, 311 divided by 7,000. Grab our calculator here. 311 divided by 7,000 is 0.0444285. So again, we're going to round that. Oh, I lost my calculator. Where'd it go? So we want to round that to 0. I don't know why that keeps closing. 0.0444. We don't want to write all of those, so we'll say 0.444. After the last 4 is a 2, so we don't need to round that up. Okay, so now that's as a decimal, that's not as a percentage. So to change it to a percentage, different people do different things when they talk about changing percentage. Some people like to think of it as multiplying it by 100. Some people like to think of it as shifting the decimal 2 spots. I tend to think of it as shifting the decimal 2 spots, but I know a lot of you have been taught to multiply by 100. So however you want to think about it is fine. But as a as a percentage, this would be 4.44%. Okay, so about 4.44% of the world's population is from the U.S. I think we tend to think of ourselves in the U.S. as a little bit bigger part of the world than we actually are. We're only or less than 5% of the world population live in the U.S. So then for number 3, it says in 2011, the population of China was 1.341 billion. Compare China's population to the world population. So if we want to do the same thing we did with the U.S. with China, so China to the world is 1.341 billion to 7 billion. And if we want to write that out with an actual number, that would be 1341. We have to be careful. Billion, if it's a whole number, we can just add on the 9 zeros, but here it's a decimal, so we have to think of it shifting 9 decimal spots. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 1,341,000,000. And then to 7 billion. Kind of squish that in there. Okay, so if we want to cancel, we can cancel these zeros with these zeros and these zeros with these zeros. And we get 1,341 to 7,000. So if we think about it, I'm not going to rewrite it again, but for every 7,000 people in the world, 311 are from the U.S. In fact, let's just add it up here. And 1,341 from China. So out of every 7,000 people in the world, 1,341 of them are from China. Then it says write your answer as a percent and as a fraction. So as a percent, again, we're just going to divide. So that would be equal to 1,341 divided by 7,000, which comes out to be approximately 0.1915, and so I'm gonna round it to this third decimal spot, but since it's a 1 with a 5 after it, I'm gonna round it to 0.192, which is 19.2%. So 19.2% of the world's population is from China. So it says next we're supposed to compare China's population to the population of the United States. And it says to write a sentence. I'm not going to take the time to do that right now, but it says, you know, so we have 4.44% versus 19%. So this is less than 5%, and this is close to 20%. So if we were to compare the 4.4%, oops, sorry about that. Let me try that again. So if we were to compare the 4.4% to the 19.2%, this is more than 5 times as much. I'm sorry. That's not more than 5 times. It's more than 4 times as much. So if we think of this as almost or not quite 5%, and this is not quite 20%, 5 times 4 would be 20%. So it's more than 4 times as many people live in China as in the U.S. And I'm going to stop this video now because it's getting kind of long for YouTube, and so there'll be a second part for Unit 2 that you'll need to watch, and I'll do the rest of 2C and then continue with 2D.